Pushing the brake pedal makes the car stop every time. Well, that's what our customers expect. Until that one day, it doesn't. Then it's our job as professionals to find out why. The why can't be answered until we know the how. That is, how a brake system works. So, grab yourself a coffee, sit back, and let's learn some of the principles behind an automotive braking system. We know the purpose of the vehicle service brakes are to slow or stop the car within a reasonable distance from different speeds. The emergency or park brake is a separate brake system designed to help arrest the car's movement through driver input if the service brakes fail. The emergency or park brake is also used to hold the vehicle stationary once momentum has ceased. System designs will vary, but some components are shared between the service and emergency brakes. Conventional automotive brake systems use friction to convert the vehicle's motion or kinetic energy into heat energy. This is achieved through a set of friction pads or linings that apply pressure to the disc rotor or drum. The more force applied between the friction material and the rotating component, the greater the level of kinetic energy converted to heat. The reduction in kinetic energy translates to a reduction in disc or drum speed. When we talk about friction created between a brake pad or lining and a disc or drum, we're really talking about the coefficient of friction between the two. Friction materials are chosen by brake system engineers based in part on their coefficient of friction value. This value changes based on the properties of the materials that are causing the friction. We can see high coefficients of friction when observing rubber tyres turning on a road surface, with low coefficients of frictions seen between ice and a glass surface. A brake material must have a high coefficient of friction when operating over a wide temperature range, but it must also be durable enough that can be applied many times without wearing away. The ideal friction material should provide consistent performance across all operating temperatures during high and low speed braking and all weather conditions. They must have resistance to pad and disc wear and produce minimal noise during operation. There are three common types of brake materials used by manufacturers. These can be grouped into organics, metallics and ceramics. While most reputable brake material manufacturers no longer use asbestos in the construction of their products, keep in mind it may still be out there in less common or cheaper brake materials. Organic friction materials contain a combination of synthetic glass fibres, aramid fibres and natural organic fibres as the main reinforcing ingredient. These materials work best at lower temperatures and normal braking conditions. A metallic friction material may contain between 30 and 65% metal, which can be a combination of steel wire and iron powder. Metallics are a good compromise between wear resistance, noise and performance. Ceramic friction materials contain ceramic fibres, ceramic type compounds and some non-ferrous metals. They offer excellent performance in all areas. They're quiet, they last a long time and they're very effective over a wide temperature operating range. The initial force used to push the friction material against the disc or drum is generated by the driver. By performing a few calculations, we can understand the concept of how this initial force is multiplied through the brake system to stop an average size vehicle. A car weighing 1,400 kilograms and travelling at 100 kilometres an hour takes around 38,000 newtons of force to stop. But the average person can only exert a force of about 500 newtons on the brake pedal. Force multiplication is used through leverage, vacuum boosting and hydraulic advantage to achieve the desired levels needed to stop the car. A brake pedal uses mechanical leverage to multiply the driver's effort or applied force to the load. A brake pedal is a second-ordered lever. We can calculate the force multiplication by dividing the total length of the lever by its working length. This example gives us a multiplication ratio of about 8 to 1. This equates to a mechanical force of 4,000 newtons now applied to the load. All modern vacuum assist units are actually vacuum suspended systems, meaning the system is balanced using engine vacuum until the brake pedal is applied. Applying the brake allows atmospheric pressure to unbalance one side of the diaphragm, generating force. The force is calculated using the pressure differential across the diaphragm, multiplied by its surface area. The pressure differential can be found by subtracting atmospheric pressure from the engine vacuum pressure. A 4-cylinder car produces about 17 inches of mercury, or 45 kPa at idle. Since atmospheric pressure at sea level is 103 kPa, our pressure differential is 58 kPa. If our vacuum booster has a diaphragm diameter of 250 millimetres, we can calculate its surface area to be just on 49,000 square millimetres. So the force applied by a booster is 2,842 newtons. Using mechanical and vacuum multiplication, we've just increased our brake force to over 6,800 newtons applied to the master cylinder. To have a true understanding of how a brake system works, we need to be familiar with Pascal's law. This law states that a change in pressure at any point in an enclosed fluid system is transmitted undiminished to all points in the system. Imagine two identical liquid-filled cylinders connected via a tube, and a given force is applied to one. The force will transfer through the liquid to the second tube without loss. Likewise, if the piston is compressed in the first tube by a given amount, the second piston will move in the opposite direction by the same amount. Non-compressible liquid used in automotive brake systems must be able to withstand the extreme temperatures produced during the energy transfer stage. Automotive systems are designed to use either a DOT fluid or a mineral oil. A vehicle's brake system has been designed to apply a hydraulic advantage at either the wheel cylinders or caliper pistons. This advantage is achieved by designing the hydraulic system with different size cylinders for the fluid to operate in. Our master cylinder is connected to the caliper piston via a pipe, just like our two plastic tubes. In this instance, the caliper piston has twice the surface area of the master cylinder piston. If we move the master cylinder 20 millimetres, the caliper piston only moves 10. The caliper has a greater volume than the master cylinder, so the piston will not travel the same distance. Even though the stroke is reduced, the force applied by the caliper piston is increased. When we look at our brake circuit, we can see the force that we originally generated with our leg has multiplied through leverage, vacuum, and now hydraulics. By applying a force of 6,800 newtons to the master cylinder, we can calculate the force applied to a single caliper within the brake circuit. Since the caliper piston has twice the surface area of the master cylinder, our input force is effectively doubled. We can now see 13,600 newtons of force applied to the brake pad, or 27,200 newtons of force applied to both front brake units. Rear calipers or wheel cylinders are generally not as large as the front. They're designed this way to allow for mass transfer under braking events. If these pistons have a surface area of the same size as the master cylinder, then there is no hydraulic advantage. The same force is applied to the rear linings or pads as applied to the master cylinder. If we do the calculations, we can see we have hit the mark of 38,000 newtons of force needed to stop our average car. When designing their systems, brake and vehicle engineers look at a lot more variables than what we've just seen. So, keep an eye out for more training in this series. Thanks for watching.